Okay, so again, we're going to start 6.4 today, and we'll be finishing this off on Monday, and then you're probably going to have your next quiz on Tuesday on 6.3 and 6.4, and then we'll be starting Chapter 7. And then after Chapter 7 will be the next exam. So this next unit is a little bit shorter because it's only based on two chapters, 6 and 7. The unit after that is also two chapters, 8 and 9. And then we'll finish off by going back and doing chapters 1, 2, and 3. Okay, so we're going to spend the next couple days talking about functions. What is a function and how can you determine whether a relation is a function or not? So if we look at these first relations, meaning all of these, they are considered to be functions, whereas the second set are not functions. So you can look at both of those sets and you might be able to kind of pick out what is different about them. And what you would see is that in the first set, in the relations that are functions, there are no x values repeating, okay? In this first table of values, all the x values are different. Same thing with the second table of values. All the x values are different. It doesn't matter that in the second table of values, you have y values that repeat. That doesn't matter. What is unique about these is that all the x values are different. Same thing with the set of ordered pair. All the x values are different. Second ordered pair, all the x values are different. Again, it doesn't matter that some of the y values repeat. It's the x values you're looking at. When you look at the graphs, once again, all the x values are different because there is no spot where any points line up vertically. All the x values are different. But when we look at the graphs on the right here, you've got x values repeating, right? In the table of values, you have x values repeating. You have x values repeating. In the ordered pair, you have x values repeating. Those last 3 points all have the same x value of 12. In the second set of ordered pair, the first 2 points have the same x value as 7. Again, this graph, you've got 3 points that have the same x value because they line up vertically. And because they line up vertically, that means you can draw a vertical line through them and it'll hit all 3 of those points. When you're looking at these other graphs, you can use this vertical line method again. And when you're looking at a graph to see if it's a function or not, if you can find any place on that graph that a vertical line hits it in more than one spot, then it is not a function. Which, this circle. There's lots of places you can drop that vertical line and it'll hit the graph in more than one spot. Same thing with this graph here. Lots of places that you can stop and drop that vertical line and it'll hit the graph in more than one spot. That means it's not a function. Same thing with that graph there. It's true for all these graphs, you can put the vertical line so it doesn't cross the graph at all. But all you have to be able to do is find one spot where a vertical line will cross the graph in more than one spot, and that means you'll have more than one point with the same x value because these x values are stacked on top of each other, right? So if you drop the vertical line there, there's 4 places where you're going to have points that have the same x value. You only have to find a place where 2 x values repeat, 2 or more. So again, to determine whether a relation is a function or not, you're looking at the x values. If any x values repeat, it is not a function. And when you have a function, you can write it in what's known as function notation. The function y equals f 4x plus 1 is written as f at x equals 4x plus 1. The name of the function is f with a variable of x. In this example, 4x plus 1 is the rule that assigns a unique value for y for each value of x. Any letter may be used to name a function. 2 examples are v at t equals 9.8 t squared, or a at r equals pi r squared. So with function notation, the variable that's inside brackets matches the variable in the equation. So this first one, f at x equals, the variable in the equation is x. This one down here, v at t equals, the variable in the equation is t. A at r equals, the variable in the equation is r. So this means that v is a function of t. You're going to put different numbers in for t to get your answer for v. Or a is a function of r. This is actually the formula for area of a circle. The area is based on the radius. The area is a function of the radius. And so that's why you have the variable r in the equation. Function notation highlights the input-output aspect of a function. The function f at x equals 4x plus 1 takes any input value for x, multiplies by 4, add 1 to give the result. For example, if x equals 2, the input, then f at 2 equals 9 is the output. And this is one of the values of function notation, right? If you're told that f at x equals 4x plus 1, and you don't want to know what the value of that function is when x equals 2, you just say f at 2, and that's what it means. You're replacing the x value with 2. So that's one of the real nice things about function notation. Instead of saying what is the value of y when x equals 2, instead of saying all that, you can just say what is f at 2, and that's what it means. It means what you get when you let x equal 2. So on the right, again, a function is a relation in which each value of the independent variable, which is x, is associated with one value of the dependent variable, y. In other words, for every value in the domain, there is a unique value in the range. Another way of saying this is that every point has a different x value. That's what you have to remember. A symbolic notation. Function notation is a symbolic notation used for writing a function. Again, f bracket x is read as f of x or f at x. And the vertical line test is what we did up here above with this vertical line that we moved all over the place. Okay? It is a test that can be used to see if a relation is a function. If any vertical line intersects the graph at more than one point, then the relation is not a function. So that first example says determine whether the relation is a function. And the first couple ones are graphs. And for graphs, we use the vertical line test. All you have to be able to do is find one spot where a graph or where a vertical line touches the graph in more than one spot, and then you would say that is not a function. For that first one, no matter where you stop and drop that vertical line, it'll only cross the graph in one spot. So that is a function. But for the second one, there's lots of places that you can stop and drop that vertical line where it hits the graph in two spots. So then when you can find at least one place where that happens, you can say that it is not a function. So the first one is a function. It passes the vertical line test. The second one is not. It fails the vertical line test. Those next two examples, you have a table of values. If any x values repeat, it is not a function. So the first one is not a function because these first 2 points have the same x value. But the second one is a function because the x values are all different. It doesn't matter that you get y values repeating. It's only the x values you're looking at. So relation E, if you compare all the x values, they are different. So that is a function. But for relation F, they all four have the same x value, so it is not a function. All you have to do is see at least 2 points that have the same x value, and you can say that it is not a function. So try those 3 on your own. Princess, is the first one a function? Want to bet a pop on that? Is she right, John? Why not? It fails the vertical line test. Those 2 points right there have the same x value. So it's not a function. Good thing you didn't bet, Princess. What about the next one, Keen? Is that a function? B. Yes or no? It is? You want to bet a pop on that? Well, you should have, because you're right.
Oh.
Why is it a function, Allie? What doesn't repeat? The x values don't repeat. It doesn't matter that y values repeat. How what? Look at the first number, -2, 0, +2, +5. All the x values are different. It doesn't matter that the last 2 points, actually the first and the last two, all have the same y value of +1. That doesn't matter. You're only looking at the x ones. Yes, sir. No, because x is -2 is to the left of the y-axis. If x is +2, that's the right of the y-axis. They don't line up vertically. It doesn't matter if they line up horizontally, because that means the y values are the same if they line up horizontally. They just can't line up vertically. So this one is a function, and Keen could have won a pop, but he has no confidence. I made what?
You scared me.
I scared you. What about the next one, Sophie? Is that a function? Yes or no? Why? All the x values are different. It doesn't matter that y values repeat. The x values are different. So let's look at some examples where we work with equations that are in function notation. The function f at c equals 1.8c plus 32 can be used to determine or convert a temperature in degrees Celsius to a temperature in degrees Fahrenheit. So again, if we write that equation out, this tells us that the temperature in Fahrenheit is a function of what it is in degrees Celsius. Because you have got c in the brackets, you've got c as a variable in the equation. So part A says determine f at 25 and explain your answer. So if you write f at 25 and compare it to what we have above, what's happened is that the c in the bracket has been replaced with a 25. Which means you're going to replace the c in the equation with 25. And then you work it out. Order of operations tells you do the multiplying before you do the adding. So 1.8 times 25 is 45. Plus 32 is 77. And what does that mean? That means that 25 degrees Celsius is equal to 77 degrees Fahrenheit. If you go down to the US, they give temperatures in Fahrenheit. They don't use the metric system. Okay? Well, I think because of the cost that would be involved in changing everything, like it's probably been about, I don't know, close to 50 years that we changed in Canada. We used to be using the old imperial system, but we changed into the metric system probably somewhere around, no, it was much earlier than that, I think. But anyways, whenever you do that, you have to change everything. So every road sign along the highways have to be changed, right? Any packaging has to be changed. Like you buy stuff and you have volume. Like if you look on that pop bottle, it says how many milliliters it is. That's the metric system. But if you bought it in the States, it would say how many fluid ounces it is. So you'd have to change everything, right? Absolutely everything. And it'd be a big cost. Okay, Now, part B says determine C if f at C is 100. So if you write the original equation out again, which is that f at C equals 1.8C plus 32. If we look back at the previous question, part A, it asked us to find f at 25. So that meant that C was 25, just the C. Part B is saying that all of f at C is 100. So f at C is what's on the left side of this equation. All of that is 100. So in this case, we need to solve this equation for C. We need to get C by itself, which we would do by subtracting 32 from both sides first. 100 minus 32 is 68. So 68 will equal 1.8C. And then to get C by itself, we would divide both sides by 1.8. And that would give us C by itself on the right, and on the left, we go 68 divided by 1.8, which is 37.8 if we round it. 37.8. Because for the other one, we were just given C. We wanted to find out what f at 25 was, which means a C was replaced with 25. In question B, you're told what all of f at C is, not just C, but all of f at C. And f at C is what's on the left side of the equation. So what does this mean? Well, f at C means that is the degrees in Fahrenheit. So what this means is that 100 degrees Fahrenheit is equal to 37.8 degrees Celsius. So very rarely does it get 100 degrees Fahrenheit here. There was a couple summers ago, at the end of June, you might remember, it was smoking hot. It was like 40 degrees. So that was over 100 degrees Fahrenheit. But it doesn't get here very often. Okay? But down in parts of the U.S. in the summertime, it regularly gets over 100 degrees Fahrenheit, especially like places like Texas, okay, Arizona, absolutely, Nevada, desert areas. So in the summertime, it gets well over 100 degrees Fahrenheit. So looking at your turn, determine f at 86. So we're using the same equation. F at C equals 1.8C plus 32. That is our original equation. And again, part A says determine f at 86, which means that you're replacing the C with 86. So you're going to let C equal 86 in the equation. So this is saying that the temperature is 86 degrees Celsius. That's what C represents, the temperature in degrees Celsius. So it never gets that hot here. And we're going to see that the answer in Fahrenheit is going to be quite a large number. And most calculators will do order of operations, so we can put it all in one step. If we want 186.8 degrees Fahrenheit is what that would be. And that's what it means when it says explain the answer. This means that 86 degrees Celsius is equal to 186.8 degrees Fahrenheit. Never gets that hot. Not even on the equator, I don't think. Okay. Part B says determine C so that f at C equals 98.6. So again, if we start with the original equation, f at C equals 1.8C plus 32. You see in the last example, in the last question, it was just C that was 86. We replaced the C with the 86. This one is saying that f at C, the whole value of f at C, the entire left side is 98.6. So this means that we're dealing with 98.6 degrees Fahrenheit We want to know what temperature that would be in Celsius. So in this case, we need to solve for C. We'll subtract the 32 from both sides. 98.6 take away 32 is 66.6. And then to get C by itself, you would divide both sides by the 1.8. Do a better job of writing that 8. And this will give us C by itself on the right. And on the left, 66.6 divided by 1.8 is 37 degrees. And so again, what that means, F at C is the temperature in degrees Fahrenheit. This means that 98.6 Fahrenheit is equal to 37 degrees Celsius. Okay, part C says another measurement scale for temperature that is used in science is the Kelvin scale. The function K at C, so the degrees in Kelvin is as a function of the degrees in Celsius. And it's given by C plus 273.15. So K at C, the degree Kelvin, as a function of the degree in Celsius is found by going C plus 273.15. So you just take the degrees in Celsius and you add 273.15, and that'll give you the degrees in kelvins. So it asks us to determine K at 80. So we're going to let C equal 80. You see, only the C has been replaced. Instead of K of C, it's K of 80. The C has been replaced with 80, so we let C equal 80 in the equation. And that gives us what, 355.15? No, 353.15, I think. Which means that 80 degrees Celsius is equal to 353.15 degrees Kelvin. Pardon? I honestly don't know. It's something in science. I do not know. Okay, so yesterday we did a bit of work with graphing linear functions. So we'll do another example today. Sky has a cell phone plan for a monthly fee of $20 plus 15 cents for each text message to or from a number not on a list of favorites. Her monthly bill can be modeled by that relation. C equals 0.15N. So that comes from the fact that it's 15 cents per message plus 20 because that is her base fee every month. So that's where the equation comes from. C is the total charge in dollars, N is a number of additional text messages. Part A asks us to write this in function notation. So remember, function notation is where you're going to have a letter and then another letter in brackets after it. And the letter that's in the brackets matches the letter in the equation or the variable in the equation, which in this case is the letter N. N is the variable in the equation. So the function notation form will be C at N equals 0.15N plus 20. So that's the only difference to write it in function notation. Instead of just C equals something involving N, it's C at N equals. That makes it function notation. Okay, Brock, you're with us? Okay. So there's A. Part B, make a table of values and then graph the function if Sky sends up to 4 additional text messages. So our table of values, I'm going to do a vertical table of values here. And you always start with the independent variable, right? The number that's inside the equation, which is the letter n. And whatever number you put in for n, that'll give you c at n. And we're going to go up to 4 additional text messages. So we might have 0 additional, or 1, or 2, or 3, or 4. And so if n is 0, and we look at the equation, 0.15 times 0 is 0, plus 20, her bill that month would be $20. And for each additional text message, it's going to be another 15 cents. So the next one will be $2.15, and then $2.30, and then $2.45, and then $2.60. And you could have got these values by letting n equals 0 in the equation, then n equal 1, then 2, then 3, then 4. But this is what you get. Okay. So we looked before at graphing, and we had to clearly show where our axes are. So that's the first thing. You have to label the axes, and remember that the first thing in the table, that's your independent variable, that goes on the bottom. This will be n, the number of additional text messages. And the dependent variable goes along the side. So that'll be C at n, the total cost, which will be in dollars. And we also have to choose a suitable scale. So for n, a scale of 1 makes sense because we started at 0 and we went up by 1s. But just so that the data isn't too close together, I'm actually going to use a scale of 1/2 here, meaning I'm skipping every second line. It just spreads the data out a little bit. Now, for C at n, if we just start at 0 here, and we try and go up by an amount that will allow us to put these values in there, we're going to go way off the scale because these values are going up by 15 cents. If you start at 0 and you go up by 15, you'll be at 15, and then 30 cents, and then 45, and then 60, and then 75, and then 90. You get up here before you even get over $1. And we have to get up to over $20. So you're going to run out of room. So here's something that we can do. We can make a break in this axis. So that's what that squiggle does. It tells us that we're skipping the first part of the y-axis here because we don't need all these values. And this allows us to start then at whatever number we want and go up by whatever we want. So I can skip a point and then say the next one is $20.15. I can skip a line and say the next one is $20.30, and then $20.45, and then $20.60. Your graphs must have your axes labeled, and you must have a suitable scale. And whatever your scale is, you have to continue that pattern. So the scale on each axis doesn't have to be the same. On the x-axis, I went up by 1s. On the y-axis, I went up by 15 cents. What's your question, Kai? $20.30, then $20.45. I'm going up by 15 cents every time. And then $20.60, going up by 15 cents every time, which matches the numbers in the table, right? So now we can graph these. We've got the point 0, 20, which is on the y-axis. 1, comma, 2015, 2, comma, 2030, 3, comma, 2045, and 4, comma, 2060. So here's the $1 million question, Keen. This is going to be a chance for you to win a pop. Are you ready for the question? Can you join these points? Can you draw a line through them? Why not? Because it's not repeating? You don't know. Does that mean you don't want to bet a pop? Sorry? You're not going to bet. So you're half right. You cannot join the points. Half right. So you get the part of the pop that has all the backwash in it. You get that half. Why can we not join these points? Why is this discrete data? Jan. Well, it is a linear pattern. They do line up. That's right. You cannot have half of a text message. You can't have a third of a text message. The price only goes up after each text message. That's why it is discrete data, not continuous. You cannot draw a line through them. Because if you did, you're saying that all values between one text message and two text messages are part of this relation, and they're not. There's no values between 1 and 2 text messages. The price only goes up after each text message, each extra one. So it is a linear pattern because it's going up at a constant rate, but you cannot draw a line because this is discrete data. Okay? I think we're going to stop there. So you guys have lots of time for your quiz. So we're going to finish this lesson off on Monday. And then Tuesday will be your next quiz. We'll also be starting chapter 7. Okay? So you should write down these questions because you should be doing these for practice. And I will put the answers for these ones on Google Classroom so you can check your work. So on page 311 to 313, numbers 1 and 4 through 8. Work on those questions for practice. And I will post the solutions.